The inverse of a product of matrices, reversal law. Hello everyone. To begin today's session, let's first ground ourselves in what we have already covered. In our previous subsections, we established the fundamental definition of an invertible matrix, understanding when a matrix possesses an inverse that allows us to return to the identity matrix. Along with that definition, we also noted a very important characteristic, that the inverse of a square matrix, provided it exists, is unique. In other words, a matrix cannot have two different inverses, there is only one. Now that we are comfortable with the properties of single matrices, we are going to move forward to a more advanced and critical property. We will be exploring how to find the inverse when we are dealing with the product of two matrices. This will lead us into the reversal law, which we will examine in detail in the upcoming slides. Theorem statement. First, let's look at the theorem. Suppose we have two square matrices, A and B, both of which are invertible and share the same dimensions, or what we call the same order M. The theorem tells us that if these conditions are met, then the product matrix, a B, is also guaranteed to be invertible. However, the way we find its inverse is quite specific. The inverse of the product, a B, is equal to the inverse of B multiplied by the inverse of A. To put this in simpler terms, the inverse of a product of two matrices is the product of their individual inverses, but they must be taken in the reverse order. Now that we have established the basics of invertible matrices and their uniqueness, let's move on to a very important property known as the reversal law. It is a common instinct to want to keep the matrices in the same order, but as we will see in the next slide, the logic of matrix multiplication requires this reversal to successfully return us to the identity matrix. Logical proof. To prove that B inverse A inverse is indeed the inverse of the product of B, we must demonstrate a fundamental property. Multiplying the product of B by B inverse, A inverse from both the left and the right must result in the identity matrix, I. Let us begin with step 1, which is right multiplication. First, we set up the multiplication by placing the product of B on the left and B inverse A inverse on the right. This gives us the expression, open parenthesis, a B, close parenthesis, multiplied by open parenthesis, B inverse, A inverse, close parenthesis. Next, we apply the associative property of matrix multiplication. This property allows us to regroup the matrices without changing their sequence. By regrouping, we can focus on the inner matrices, rewriting the expression as A multiplied by the quantity B times B inverse, multiplied by A inverse. Since we established in our theorem that B is an invertible matrix, we know that B times B inverse equals the identity matrix. I substituting this in, our expression becomes A times I times A inverse. Now, recall that any matrix multiplied by the identity matrix remains unchanged. Therefore, A times I is simply A. This simplifies our expression further to A times A inverse. Finally, since A is also an invertible matrix, A times A inverse equals the identity matrix, I. Having proven the right side, we must now perform step 2, left multiplication. Here, we multiply from the left by placing B inverse A inverse first, followed by the product of B. Again, we use the associative property to regroup the matrices. This allows us to isolate the inner terms, giving us B inverse, multiplied by the quantity A inverse times A, multiplied by B. Since A inverse times A equals the identity matrix, I, the expression simplifies to be inverse times I times B. As we noted previously, the identity matrix does not change the matrix it is multiplied by, so this further simplifies to be inverse times B. And since B is invertible, B inverse times B equals the identity matrix, I. To conclude, since multiplying a B by B inverse A inverse from both the right and the left results in the identity matrix, we have met the formal definition of an invertible matrix. This proves that B inverse A inverse is indeed the inverse of a B. Therefore, we can confidently state that the inverse of the product of B is equal to B inverse A inverse. Now that we have stated the theorem, let us move on to the logical proof to understand why the order of matrices must be reversed. In the next slide, I will share a real-world analogy to help you visualize why this reversal of order is so intuitive. Conceptual analogy, real-world example. Now that we have examined the formal logical proof, you might be wondering why the order of the matrices must be reversed. To make this concept more intuitive, let us consider a real-life sequence of actions. Imagine we have two distinct operations. Let us define operation A as the act of putting on your socks and operation B as the act of putting on your shoes. In matrix terms, the combined operation AB represents the sequence of these events. First, you put on your socks, and then you put on your shoes. Now, if we want to undo or invert this entire process to return to our original state, which in this case is having bare feet, think about the physical order required. You cannot take off your socks while your shoes are still on. Therefore, you must first perform the inverse of operation B, which is taking off your shoes, denoted as B inverse. Only after the shoes are removed can you perform the inverse of operation A, which is taking off your socks, denoted as A inverse. Consequently, the inverse of the combined process AB is the product B inverse A inverse. This illustrates the core logic of the reversal law. The last action performed is always the first action to be undone. With this conceptual understanding in place, we can now move forward to the next slide to verify this law using a concrete numerical example. Numerical example. Now that we have discussed the theoretical proof and the conceptual analogy of the socks and shoes, let us move on to a numerical example to verify the reversal law in practice using 2x2 matrices. First, let us look at our given matrices. Matrix A consists of 1 and 2 in the first row and 0 and 1 in the second row. Matrix B consists of 1 and 0 in the first row and 3 and 1 in the second row. We will begin with step 1. Finding the product of A and B by multiplying matrix A by matrix B, we calculate the elements row by row. For the first row, we have 1 times 1 plus 2 times 3, which gives us 7, and 1 times 0 plus 2 times 1, which gives us 2. For the second row, we have 0 times 1 plus 1 times 3, which gives us 3, and 0 times 0 plus 1 times 1, which gives us 1. So, the product matrix AB is a matrix with 7 and 2 in the first row, and 3 and 1 in the second row. In step 2, we find the inverse of this product matrix, denoted as the inverse of a B. To do this, we use the standard formula for a 2x2 inverse, which is 1 divided by the determinant, multiplied by the matrix where we swap the main diagonal elements and change the signs of the empty diagonal elements. The determinant of a B is 7 times 1 minus 2 times 3, which equals 1. Since the determinant is 1, the inverse of a B is simply the matrix with 1 and negative 2 in the first row, and negative 3 and 7 in the second row. Now, for step 3, let us find the individual inverses of A and B separately. For matrix A, the determinant is 1 times 1 minus 2 times 0, which is 1. Therefore, the inverse of A is a matrix with 1 and negative 2 in the first row, and 0 and 1 in the second row. Similarly, for matrix B, the determinant is 1 times 1 minus 0 times 3, which is also 1. This gives us the inverse of B as a matrix with 1 and 0 in the first row, and negative 3 and 1 in the second row. Finally, in step 4, we calculate the product of these inverses. Crucially, according to the reversal law, we must multiply them in the reverse order. The inverse of B times the inverse of A multiplying these two matrices, we get 1 times 1 plus 0 times 0 for the first element, which is 1. 1 times negative 2 plus 0 times 1 for the second, which is negative 2. Negative 3 times 1 plus 1 times 0 for the third, which is negative 3. And negative 3 times negative 2 plus 1 times 1 for the final element, which is 7. This results in a matrix with 1 and negative 2 in the first row, and negative 3 and 7 in the second row. If we compare our results, we can see that the inverse of the product of B is exactly the same as the product of the inverses in reverse order, B inverse times A inverse. both result in the same matrix. This numerically verifies the reversal law. Keep this specific order in mind, as we will discuss in the next slide why ignoring this sequence is one of the most common mistakes students make. Common mistakes. First, let's address the issue of ignoring the order. The most frequent error students make is writing that the inverse of the product of b is equal to the inverse of a multiplied by the inverse of b. This is incorrect. As we have established, matrix multiplication is not commutative, which means that the inverse of a times the inverse of b is not the same as the inverse of b times the inverse of a in most cases. Always remember to reverse the order. Secondly, be cautious about assuming invertibility. It is common to apply this law automatically without first checking if matrix A and matrix B are actually invertible. Please keep in mind that this law only holds if both individual matrices possess inverses. If either matrix is singular, the product cannot be inverted in this manner. Finally, regarding the logical proofs we practiced earlier, be mindful of the multiplication order. When you are demonstrating the proof, ensure that you multiply by the inverse of the inner matrix first. This is the critical step that creates the identity matrix, allowing you to simplify the expression and complete the proof successfully. Now that we have seen the reversal law in action through both a logical proof and a numerical example, it is important to discuss some common pitfalls to ensure you avoid these mistakes in your exams. By staying mindful of these 3 points, you will avoid the most common errors associated with this topic. Now, let us move to the final slide to summarize our key takeaways. Key takeaways. To wrap up our lesson, let's go over the key takeaways to ensure you have a solid grasp of this concept. First, let's reiterate the reversal law. For any two invertible matrices, A and B, the inverse of their product, expressed as the inverse of a B, is equal to the inverse of B multiplied by the inverse of A. As we emphasized in our discussion on common mistakes and through our socks and shoes analogy, the order of operations is critical. You must remember to swap the order of the matrices whenever you distribute the inverse sign across a product. Regarding the requirements, please keep in mind that this property is not universal. It is only applicable if both matrices are square and, crucially, if both are invertible. If either matrix lacks an inverse, this law cannot be applied. Finally, it is important to note that this principle generalizes beyond just two matrices. The reversal pattern continues regardless of how many matrices are in the product. For example, the inverse of the product of A, B, and C is equal to the inverse of C, times the inverse of B, times the inverse of A. Essentially, you always reverse the entire sequence.